I'm going to look at setting up a power feed to go on this mill.
Compared to previous videos, this project will be a lot more in-depth with more technical content. Because hey, let's alienate the established audience. The intention of this project is to mount a stepper motor to drive the x-axis of the mill here.
So this power feed is going to be smart. It's going to be Arduino powered. So somewhere we're going to have a control box. I've yet to decide where. There will be a plate coming down with a gearbox and a clutch assembly inside it. And then the stepper motor will be pointing out at 90 degrees. And that's just for some space limitations around my machine. I'm also going to have to think about the interaction with the hand wheel. But I'll go into a lot of the placement details in the next video. This video will just focus on the electronics themselves and just getting everything wired up.
Say hello to the new electronics workstation.
So the setup we've got an Arduino. It's sending out pulses to the stepper driver to control the speed. The rate of these pulses is controlled by a potentiometer. And over here I've just got a push button that I'm using to change the direction. At the moment I've just got a push button. In the actual build I'm going to have a pair of limit switches.
Yeehwah!
So limit switches. There's two ways you can wire them up. There's normally open, which is an open circuit until the button is pressed, and then there's normally closed, which is always sending a signal until the button is pressed. I'm going normally closed because this has a few advantages. If the circuit is constantly sending a signal, if a wire or a connection comes loose, the limit switch will trigger. The other way, if something breaks, the mill table is going to keep ploughing through everything, waiting for a signal that's never going to come. And that would be bad. This is our control panel plate in Fusion 360. For the most part, it's just 2D contours. These inner plugs where the electronics will go will fly out. I'm not really concerned with this because I'm just cutting thin material here. There's only minor risk for tool breakage.
So I've gone ahead and so I've progressed further with this. I figured people wouldn't really be interested in seeing the trial and error trying to get this set up, so I might just take you through the final. Let me show you the operation. So plugged in. This is direction indicator, left or right, and at the moment it's just in a hold on startup. We have our hold button here. That's the get ready. Set your speed, set all your settings, and go. So speed change button. This is our rapid and rapid speed. We can hold at any time. There's also a pair of limit switches. These will be attached to the table. So the limit switches are able to bounce the table backwards and forwards. Now these buttons here are toggles. They're actually wired backwards at the moment. But if I hit this one, everything stops until you hit the direction button. So let's back up a step and discuss button wiring.
Now I've got a couple of these switches to wire up.
5 pins, what do you do? Not this.
It looks a bit confusing at first, but when you understand it, it's pretty straightforward. So this is the positive and the negative to the light. These are illuminated buttons. Now if you connect these pins up, the light will turn on and the button press means nothing. These 3 pins depend on the button state. Starting at the bottom, the common is always connected to the switch. I'm going to run the positive into here. You have normally open, so it's an open circuit with no connection until the button is pressed. This one is normally closed, so when the button is not pressed, it's on, and when the button is pressed, it is off. It is opposite to normally open. So at the moment, if I run power into the common, I'll get power out of the normally closed and nothing out of the normally open. If I push the button, closed turns off and the open turns on. And that's what I want, but I want my light to come on at the same time. So the positive and the negative go to the light. So what I can do, I could put a jumper between these pins, or alternatively, I could bend it in and solder it straight on. So connecting the positive to the common, when the button is pressed, power out of the normally open, and it goes into the positive to the light. Then we connect our negative up to the light's negative.
At this stage, we've got a pretty ugly mess of wires here. We might make it a bit better. I think the next stage in this process is to make a proper control panel.
So we've got some technical issues. So many hours of screwing around have been spent to output this plate. So the issue I've got, when the spindle is running and the end mill is touching the aluminium plate, I'm getting some crazy interference which is shutting off electronics. I've never had this happen before when cutting MDF. My first thought, we've got a grounding issue. Connected to my VFD, I've now got a ground going to the table. In my Arduino, stepper driver and power supply, I've got all that connected to the table also. I've also grounded my machine and the workpiece to the table for extra measure. And the result? Still not working. So I tried disabling limit switches, still no go. So my thinking is each time the end mill is making contact with the workpiece, it's momentarily increasing the voltage potential of the entire plate. So each time the cutter comes around, the cutting flute makes contact, we have a circuit, it finishes the cut, and the circuit is disabled. This router bit is spinning really fast, so we're getting a fluctuating signal on and off, on and off, on and off. So we'll get a sinusoidal or probably a square wave signal. I think the workpiece is becoming an inductive transmitter, which all the electronics are picking up and getting false signals. So to output the first plate and test it, I decided to short it out so we wouldn't get the fluctuating signal. And the way I did that, I jammed a shifter up against the spindle body and against the workpiece. It worked absolutely fine. I'm going to fabric cobble a grounding plate to follow around the machine and try it out on this next piece.
It's unconventional, but if it works, I'm running with it. Ta-da! Success! Okay, after all the effort of wiring this up, now I've got to unwire it and transfer it all to this plate.
I'm going to try and preemptively answer some questions. So motor selection. So first of all, does this need to be a stepper? No. This is future proofing if ever I decide to switch the mill to CNC or have a large production run. I can create a special program on the Arduino and run a pre-programmed sequence. So the other question, what size motor and how do you determine it? This is a 3 Newton meter stepper. So how do I work out the load required? On my mill, I measured the hand wheel offset. So when I'm cranking this, I'm applying a force at a distance. So I cranked this a few times and felt the maximum force I'd normally experience. I then went to some bathroom scales, pushed down, measured the same force and compared it against stepper motors. But I think I got 1 Newton meter at a very extreme measurement, and then I decided to triple that for good measure. Very scientific. So in terms of Arduino and code, I've left that out of this video. Kind of thought it wouldn't really make a very interesting video, but hey, if enough people are interested, maybe I'll consider doing a video on the program.
Well, I guess that's about it for this video. Next video we'll look at setting up the gearing and housing for all of this and a clutch assembly. Also, feel free to leave a comment if there is anything that does or doesn't work in these videos. Catch you later.